So, good afternoon, everyone. So, I think last class we talked about electrochemistry only, but today also we are going to extend the electrochemistry, but another part of electrochemistry, that is your conductance portion, right? So, we focused upon electrochemical cells and all in the last class. Today, next slide, please. Today we are going to focus upon mainly conductance and electrolytic cells and their applications and all. Next slide, please. So basically these are the areas that we are going to cover: conductance of electrolytic solutions, and some definitions like specific conductance, equivalent conductance, molar conductance, their variation with concentration, then Kohlrausch law, and then electrolysis. And there are, Faraday's laws of electrolysis. These are the portions that we are going to cover in today's class. Next slide, please. So first of all, when we talk about conductance, so the very first thing that comes to our mind is that what type of substances are there which can conduct electricity and which are responsible for electrolysis, right? So we call such substances as electrolytes, right? How do we define them? Like those substances which when taken in the aqueous form, I mean, we can take the solution also of those substances, and we can take them in molten state also, right? Liquid form of some salts we can take, and then when electricity is passed through them, they split into ions, right? They decompose, they split into ions, and those ions are responsible for conduction. So such type of substances which decompose into different ions on the passage of electricity, they are known as your electrolytes. Examples we have: typically salts. All salts are in fact strong electrolytes. Later on we will discuss what are strong and weak electrolytes, but salts, acids, right, and bases, these are the substances. Obviously they will split into different ions, cation and anion, when you pass electricity through them. And another type of substances which are your, if you define electrolytes, we have to define non-electrolytes as well. Non-electrolytes are those which do not split into ions, right? The decomposition is not possible, means it's not easy to get cation and anion out of them, so they will remain as such, right? So they obviously, when they do not decompose into cation and anion, they do not conduct electricity, right? Or so you take, sugar solution. That is the difference between salt and sugar. You daily come across such things in your kitchen, right? So NaCl, salt, if you dissolve, it will split into what? Sodium ions and chloride ions, right? So this is a very good example of electrolyte, right? And sugar, you dissolve it, you check the composition, it is going to remain the same as such, means it will dissolve, you will get a solution, but it's not like that sugar will decompose into different ions. So this falls under the category of non-electrolyte. Similarly, we can have urea also. Sugar, glucose is an example of sugar only itself. Next, please. Then we come to, when we are clear that what are electrolytes and non-electrolytes, then the next thing is that what are the different types of electrolytes, right? You can have many electrolytes, but all of them, they do not decompose to the same extent, correct? So on the basis of their extent of decomposition, or we can say on the basis of their degree of ionization, on decomposing them we get ions, right? So we define what? Degree of ionization. I mean, how, to which extent they can form ions, or to which extent they can dissociate, we call it degree of dissociation also, degree of ionization also. So on the basis of that, they are divided mainly into two types: strong electrolytes and weak electrolytes, right? So strong electrolytes are those electrolytes which decompose into ions, cation and an ion very easily. Very easily. Also, the main difference is, obviously the weak is also going to split into ions, but the major difference between strong and weak is that strong electrolytes, they decompose completely or they dissociate completely at all concentration, right? At all concentration means, suppose I take 1 molar solution of KCl, then also you get, it is fully dissociated. You have 1 mole of potassium ions and 1 mole of chloride ion, correct? That is the difference that we have in, see, you have KCl, it will split into K plus and Cl minus, right? So suppose you take 1 mole of this, then because KCl is a strong electrolyte, you are going to have what? 1 mole of this and 1 mole of this, because it is completely. So whether you take 1 molar solution, you take 0.001 molar solution, or you take 2 molar, 3 molar, 5 molar solution, you are going to get the same number of cations and anions, because it is fully dissociated. So if it is fully dissociated, we can also say that it is 100% dissociated. So therefore the degree of ionization is how much? It is 1, right? So strong electrolytes are those electrolytes, it is basically the difference in the concentration, that they are dissociated completely at all concentration. For example, you have HCl, H2SO4, NaOH, KOH, KCl, NaCl. Moreover, one more difference, that if you do not know, you come across any such substance, and then you have, if you have to write the dissociation for strong electrolytes, see, I just put a single headed arrow here. This in itself indicates that KCl is a strong electrolyte. Why? Because this reverse reaction is not possible unless we supply some energy. Reverse reaction of course can be performed, but then this forward reaction is what? Spontaneous, right? So and then we have weak electrolytes. Weak electrolytes, they also decompose to give you cation and anion only, but they are not dissociated completely at all concentration, right? So example you can take of acetic acid, all your organic acids. So here I put the sign of equilibrium. So I have CH3COO negative plus H plus ions. See the difference. You get H plus ion by the dissociation of HCl also, H plus and Cl minus, and you get H plus from the dissociation of acetic acid also. But HCl is a strong acid and acetic acid is a weak acid. Why? What is the difference? The difference is in the degree of dissociation. HCl is fully dissociated at all concentration, means whether you take the concentrated solution or you take the dilute solution, you are going to get equal number of H plus and Cl minus ion, whereas this acetic acid is not fully dissociated at all concentration. It has equilibrium, this equilibrium sign. This equilibrium sign says that there is some possibility of acetate ion and H plus ion to recombine and form acetic acid. So ions and electrolyte, they are in what? Equilibrium with each other. So such electrolytes, we call them as weak electrolytes. The degree of dissociation in this case would be what? It will always be less than 1. Carbonic acid is there, H2CO3 is there, NH4OH. You differentiate between strong acid, weak acid. Acetic acid, example of weak acid, HCl, strong acid, and then weak base, ammonium hydroxide, strong base, sodium hydroxide, right? So things like that you have, based on the degree of dissociation, you divide them. Next slide please. And then this is, we talked about what are your electrolytes and non-electrolytes, right? And in this we also saw that what are your strong and weak electrolytes. Now we basically have to differentiate your electrolytic conduction from metallic conduction, because conduction can happen in many ways, right? Means passage of electricity could be because of different reasons. So here we know that in electrolytes the conduction of electricity is because of what? The passage of, because of the movement of ions, right? Because you have ions, right? And how they are different from, there are two different types. Metallic conductors are there, and you know that any metal piece, metal wire, all your electrical wires, you know that they are mainly made up of what? Metals only. Copper wire is there, silver wire is there, right? So all those different type of wires, if they are there, they are made up of what? Metals. So it means, and moreover you know from your previous knowledge that metals are what? Good conductors of electricity. So conduction is happening in metals also, and conduction is happening in electrolytes also, in solutions also, basically I want to say. So what is the difference? In metallic conductors, there is no decomposition of the matter. The substance or the sample that you take, it is not like that if you take a copper wire and you pass the electricity, it will decompose, right? It's not like that. It will remain, the matter will remain intact. It is not, means there is, in other words we can also say that there is no chemical change. Chemical reaction is not there in metallic conductor. Whereas in electrolytic conduction, you have what? The matter is decomposed. You take NaCl, it will decompose into sodium ions and chloride ion. You take HCl, it will decompose into H plus ion and Cl minus ion. And as a result of the movement of ions, you get electricity. Electricity is conducted, right? In that difference we've already considered, that in metals it is because of the flow of electrons, because all metals, they have what? Loosely held electrons, or you can say that they are free electrons. Metal have very high tendency to lose electrons, right? So those loosely held electrons are always present, uniformly distributed on the surface of metal ions, metal sheet. If you take a metal sheet, then there is what? All your electrons, they are distributed uniformly, right? So they are mobile electrons, they move from one place to another place. So you know that flow of electrons means flow of electricity only. And moreover, one more difference is there, that you may have learned about metallic conduction in physics also, and you must have seen their variation. You know that resistance is there. Metal, they have some resistance also, right? So that resistance, it increases with temperature, right? And metallic conduction therefore decreases with increase in temperature. If you increase the temperature, metals are going to conduct lesser electricity, right? And moreover, this electrolytic conduction shows opposite trend. You have electrolytes, they conduct more electricity at higher temperature. It is obviously because of more ionization which can happen at higher temperature, right? Next slide please. There are some basic terms when we study the conductance. We talk about conductance of solutions and all, but the basic terms we must know, that is what is the difference between what is resistance and what is conductance, what is the difference between the two. If you understand that thing, then specific conductance, equivalent conductance, molar conductance, that is, there you only have a difference of concentration terms in which they are expressed. Basically the quantity is going to be the same, right? So resistance, all of you know that it is nothing but it is the obstruction to the flow of current. A current is flowing. So if you have like this, you have a uniform cross sectional area, you have a tube like this or a wire like this whose area of cross section is A and the length is L, and we know that resistance of any such wire or a cross section is directly proportional to the length So in physics you get such questions, right? Multiple choice questions also they are there, that you have different wires of different length, then which will offer more resistance, right? So obviously the wire which is having more length will offer more resistance, and which has lesser area of cross section will offer more resistance, right? So therefore, so removing this proportionality, we put a proportionality constant here which is called rho. This is called your resistivity, or you call it specific resistance, right? So how do you define this specific resistance? We can define it from here only, that rho is equal to R if L is 1, if A is 1. If you take the length and area of cross section as unity, then your rho will become R. So therefore you define that your specific resistance or resistivity is the resistance of a wire whose cross sectional area is 1 centimeter square and length is 1 centimeter, right? You can express it in SI units also. Next please. Now in metals we mainly talk about resistance and all, right? What is the resistance, how do we measure resistance? Mainly that term is used more frequently. But when we talk about electrolytic conduction, right, we talk about conduction by solutions, then you should know what is resistance, but then the conduction by ions, mainly you will use the term conductance only. You will come across conductance only, right? Because it's easier to measure, right? Conductance of solutions, you have some experiments also which can be performed in order to calculate the conductance and all. So you must know. So conductance, it's very simple, that it's nothing but it is reciprocal of your resistance, right? So C is 1 by R, and conductors, based upon to what extent means conductance is there. So it means we are talking about materials which can conduct electricity. So there are materials which can conduct electricity to different extents. Based on their conductance value, it means based on their conductance value, they are divided into mainly how many types of conductors you can have. You have mainly, 3 types, not conductors, but then based on their conductance value, you can say that conductors are there, semiconductors are there, and insulators are there. And one more class is there, we call them superconductors. Superconductors, you must have come across the term superconductors, which can conduct electricity to a large extent. You maintain certain physical conditions like very low temperature. Certain materials, they have some special properties that they conduct electricity to a greater extent when they are kept under special physical conditions. They are called superconductors, right? But normally we have conductors, right, which can conduct electricity to larger extent. Semiconductor also, like silicon, germanium, they are there, right? And semiconductor, physics may you learn a lot, N type semiconductor, P type semiconductor, what is a logic and all. And then there are insulators which do not allow the electricity to pass through them at all, right? So like similar to resistivity, when we define conductance, we define conductivity also. Next slide please. We have specific conductance. So just whatever you've done in resistance, just take the reciprocal of that, and here you know that obviously you will say that if resistance is directly proportional to the length, conductance is inversely proportional to the length and directly proportional to the area of cross section. Therefore, we define a new quantity which is 1 by rho, that is called your specific resistance, or specific conductance, or you call it conductivity also. So conductivity is represented by kappa, right? This is 1 by rho, and rho you already know that it is A R by L. So therefore from this expression you have this thing that L by A and 1 by R, you can say that it is C. So conductance. So kappa, that is your specific conductance, is equal to L by A into conductance. Therefore, right. So this L by A is a quantity that entirely depends upon the dimensions of the what? Conductor, whatever conductor you have, right? I mean, cell. Basically, let me tell you one thing, that when we talk about electrolytic solutions and all, conduction by electrolytes, then we are mainly dealing with solutions or molten state. So we are not talking about wires and all. So now we are, instead of defining it in those terms like cross-sectional area 1 and length 1, we instead define it in terms of volume. So you can also say it's better to define that specific conductance or conductivity is the conductance of 1 centimeter cube of a solution, right? Solution phase, because you are talking about. So when we talk about solution, we have express it in terms of volume. So that is there, and this L by A is called cell constant, right? Usually this cell constant for a particular cell, I'm saying cell, why it has given a name cell constant, because there is an instrument which is used to measure the conductance. That instrument is known as conductivity cell, right? And what are the dimensions of that cell in which we take the solution and measure its conductance? So it is representing the length and area of cross section of that cell. That is why it is describing you the dimensions of the cell. That is why we call it cell constant. And for a particular cell, L by A is also, it is always going to be a constant quantity, right? So there are different ways to measure cell constant also. In fact, an experiment is also there. So how do you get this quantity specific conductance? You can have this constant value of cell constant and measure the conductance of the solution. You get the specific conductance. And in fact, how do you measure this? Because I told you that this is very easy to measure, conductance, right? But this is not very easy to measure, right? So, but what can be done, that a simple experiment can be performed, in which what you can do is that you can take up a solution whose specific conductance is known at various concentrations. So usually the solution of KCl is taken for that purpose, right? KCl solution it's like a standard solution in conductance experiments, because the specific conductance kappa value for KCl is known at various concentrations, right? If it is known, then from the instrument, when you put you have a known solution whose conductance is known, and you put an unknown solution, so you will get the value of conductance from there, from the instrument. So specific conductance is known to you, conductance you measure from the instrument, so you can measure what? Cell constant. So once you have established this quantity, the value of this quantity, that is L by A, then it's easier. Rest all solutions, irrespective of their nature and all, you can use, because you know this quantity, what is L by A, right? So this is how experimentally we measure the cell constant, right? So we make a table, right, like this. Kappa value is, it's known, and then C value you measure. From kappa and C you calculate L by A. Now if L by A is known to you, then obviously it is not going to change if you change the solution. If instead of KCl you take NaCl, you take HCl, you take H2SO4, any solution, any electrolyte you take, you measure the conductance, then you can measure its conductance you get from the solution. Multiplying it with cell constant, you get what? Specific conductance, right? And the units, you know that in physical chemistry we have to be very, very particular about the units. So conductance, you know that it is opposite of resistance. Resistance is measured in ohm. So this is ohm inverse or more, or you can Siemens also. And specific conductance, you can put the units of length, area of cross section and conductance. So you have in SI you have Siemens meter inverse, or more conveniently you express it in terms of ohm inverse, centimeter inverse, right? Because see, units are always selected. It is not always that when we write any quantity that we always, I mean, it's okay that you know that SI units are, you know, standard units, and we take that, but it is important to maintain the uniformity of the units. Means whatever quantities are involved, you take the same units of all. Means if length is expressed in meter, then area meter square and all those things. But the final quantity, means suppose I am talking about kappa, it is not necessary. The units are selected as per their convenient range of the values, right? If the values are very, very small in SI, then it's better to express them in CGS system or any other system. For example, you take the simple example, no? If concentrations are too less of a solution, so you learn about various terms. Molar solutions are also there. Then you have millimolar solution, micromolar solution, and if it is very, very dilute, like you know pollutants in the environment, you express it in terms of what? ppm, right? So units are, so what, why can't you do, you can express your concentration of pollutants also in terms of molar, but then that quantity is going to be very, very less. That is out of this thing, I should not have discussed, but I am telling you that the convenient unit in which specific conductance is measured as your ohm inverse, centimeter inverse. Next slide please. And then we have equivalent conductance, right? Specific conductance means we specify the volume. We have specified that is your 1 cc. The volume is what? 1 cc, right? 1 centimeter cube solution is taken. The conductance is known as specific conductance. Now, if in that particular, so it's a equivalent conductance, the name itself says that you are specifying what? The quantity of electrolyte, right? How much is the quantity of electrolyte? It is 1 gram equivalent. Now, if 1 gram equivalent of an electrolyte is taken in any volume, in say V volume, then all ions which are produced or which are furnished by 1 gram equivalent, the conduction caused by all those ions is known as equivalent conductance, right? It is represented by lambda, means lambda EQ stands for equivalent conductance. We have this relation. Now how do we establish this relation? Lambda equivalence is given by kappa into V. From where this 1000 factor and normality factor is coming, do you know that? It's very, I mean, see, this V is representing the volume, right? Volume in which 1 gram equivalent of electrolyte has been taken. For example, how do you calculate? See, you take any solution, you take 1 cc of that solution. What will you say, what will you call that quantity rather? If you take 1 cc of any solution, right, forget about the concentration, you're not worried about the concentration. If 1 centimeter cube of solution is taken, what will you call that quantity? Conductance. You'll call it specific conductance. Just now we defined that conductance of 1 cc of solution is known as specific conductance. There you do not define the quantity of electrolyte. What are you defining? You are defining the volume of solution, right? Suppose you have, there is a cube, sorry, see 1 cc is its volume. You have a say you've taken 1 cc of solution here. Dimensions of this cube are 1 1 1 1 1, and you are not bothered about what is the amount of electrolyte that you have put into this container. So only if the dimensions are 1 cc you will call it specific conductance. The conductance offered by this solution is known as specific conductance. Now what you do, that you put 1 gram equivalent of an electrolyte into this. What will be the conductance of this solution? You will have what? It is kappa, specific conductance is there, and you will multiply it with the factor, that is the volume of solution which contains 1 gram equivalent, right? So if it is the case, if in 1 cc only you put 1 gram equivalent, then your volume is going to be what? 1 only, na? So but if you dilute that solution to V liters, to say 1 liter, then a factor of 1000 comes, right? So it is because normality is what? Gram equivalents per liter. That is why that liter goes in the numerator. So simple thing, you take 1 cc of solution, you call it specific conductance. You multiply, you put 1, when you define you decide the quantity, you put the 1 gram equivalent, you will call it equivalent conductance. You will call it equivalent conductance of V liters of solution, right? So that is why liter means per liter is there. So liter 1000 factor is coming in the numerator. So in the denominator, so simple thing that you can define that it is kappa into 1000 by normality, where you have to be careful that V, here I wrote V and here I wrote 1000 by normality. So V is the volume of the solution in cc that contains 1 gram equivalent of electrolyte, correct? Next slide please. So similar to your equivalent conductance, you have molar conductance. So if you define or take, instead of 1 gram equivalent, you take 1 mole of an electrolyte, the same quantity you will call it molar conductance, right? So it is conductance which is offered by all ions which are furnished by 1 mole of an electrolyte when dissolved in V liter of solution, right? So again you are going to get the same relationship, but the quantity is 1 mole instead of 1 gram equivalent. So therefore in the new denominator you are going to take molarity instead of normality, rest everything is same. So you see that if you perform a simple experiment, like just I told you that you can calculate the conductance from an instrument, look at the number of quantities that you can calculate from simple conductance value only. You've calculated conductance from the solution knowing the cell constant value, right? And if you measure the conductance, you can calculate specific conductance. If you know the specific conductance, you can calculate equivalent conductance and molar conductance also, right? And later on you will realize that if you calculate molar conductance also, you can calculate various other quantities also, like degree of dissociation, ionization constant, all those things, right? Next slide please. And then once we know that solutions, they conduct electricity, then we must know what are the factors which affect the conductance of solutions, right? Electrolytic conduction, it is, see, you put you put an electrolyte into a certain quantity of solution, you have different substances, right? Do all of them conduct electricity to the same extent? No, because you look at any book, any table, you'll find that there are various substances which conduct electricity to a different extent, means their conductance value is even even simple water which you take, water also splits into H plus ion and OH minus ion, but the value of kappa or conductance that you get, it's very very less, because the dissociation of water at normal room temperature is what? It is very very less. It is poor electrolyte, you can say weak electrolyte water. Right? Now these are the various factors upon which this conductance depends. First of course, that is your nature of electrolyte. This I think we've already discussed in detail, that some electrolytes we call them strong and some are weak. So obviously strong are going to conduct more electricity compared to weak ones. Correct? Then you have the size, right? Size of ions. Correct? So if if you have same quantity of solution, means same quantity of electrolyte, same volume of container in which you are taking the solution, even then they conduct electricity to different extent, right? It is because of the size, because their conduction depends upon their size also. Obviously smaller ions, they are able to move faster because they are light, right? They can travel through the solution very easily. That's why smaller ions, they conduct electricity to a greater extent compared to your larger ions. Moreover, here one more phenomena, you'll come across certain typical examples in which I've not written here, but then that also you should take into consideration, size as well as their degree of hydrolyzation. So if the size of cation, if it is very very small, then they have also tendency to get hydrolyzed. Hydrolyzed means solvent molecules are also associated. So what happens, that a small cation is there, right? See, like this, if you have small cation, then water molecules like this, they also gets associated with, and this tendency to get hydrolyzed is more if size of cation is small. Smaller cation have higher degree of hydrolyzation. Now you will expect that a smaller cation will conduct more electricity compared to the bigger one, right? But because of this solvent molecules associated, the effective size of this ion becomes bigger, larger. So while measuring the conductance of solution, you will not measure only the size of cation, rather effective size. So because its effective size is large, therefore it will move slowly through the solution and will conduct lesser electricity, right? So when we take into account the effect of size, we have to consider the effect of hydrolyzation also. Then next is your nature of solvent and viscosity, right? So it's not, because you know that certain solvents, they are what? You have different categories of solvents, na? So based on their polarity values, some are polar, some are non-polar. So obviously polar, if you have polar solvent, right? And what is the nature of your electrolyte? Electrolyte is also polar, na? Because once you put it into the solution, it will split into ions. You have dipoles, right? So polar and polar interactions are always what? More. So therefore there is a natural tendency of electrolytes to split into ions. I mean, the dissociation is more in the presence of polar solvents compared to your non-polar. So if you take water as a solvent, you'll have more dissociation compared to any other non-polar like benzene and all other solvents, organic solvents, like they are non-polar solvents, right? Equivalent conductance once again. So equivalent conductance, as I explained, that if you take if you specify the quantity of electrolyte as 1 gram equivalent, then the conductance offered by all those ions is known as your equivalent conductance. Means 1 gram equivalent of solution of an electrolyte is taken in V volume of a solution, then conductance offered by that solution is known as equivalent conductance. Then the next thing is your nature of solvent and viscosity, right? Some solvents, they are more viscous and some are less, right? So obviously if the solution, if the solvent is what, viscous solution, and then it will be difficult for the ions to travel through that viscous solution. So therefore obviously the conduction is going to be lesser in viscous solutions. So more is the viscosity, lesser will be the conductance. And next is concentration. Concentration is also important, but this is more important in case of weak electrolytes, because strong, I told you that strong, irrespective of concentration, they are fully dissociated at all concentration, right? So normally, but forget about strong and weak now, normally if you talk in terms of general electrolyte, you will say that with concentration conduction decreases, because if you have dilute solution then conductance is more. We will obviously see what are the reasons. And then finally the temperature. So temperature, already we have seen that if you have higher temperature the conduction is more. At higher temperature ions are, they have high kinetic energy, so they move faster, they move fast, they conduct more electricity. So at higher temperature conduction is more. Next slide please. The next we see what is the variation, right? Concentration, just now I told you that the dissociation depends upon the concentration, right? So you see here that we have a plot, right? So it tells us the variation of conductance with concentration. So this x is, see, we have square root of C. Why square root of C? That also I take, that comes from the equation that is being followed. Concentration dependence of molar conductance is given by d by Huckel theory. I have it in my slide. So therefore you have a dependence, you don't plot C, you plot here root C. It is root C if you observe in many books. And here you have molar conductance on y-axis. Now you see that if you molar conductance and equivalent conductance, the trend is going to be the same, right? Because it is only the quantity of electrolyte that you measure is different, otherwise they are like similar quantities, fine. So if you measure, you see that on this axis the concentration is increasing. So it means if you go right to left you are diluting the solution. So with dilution conductance increases. You take the dilute and dilute. So at zero, at zero you should have the limiting value of the conductance, that is called lambda infinity or lambda naught also sometimes, right? So this is the finally limiting value, and so it means molar and equivalent conductance. This has the similar trend that it will increase on dilution. So with increasing the concentration they decrease. Whereas when we talk about the specific conductance of a solution decreases with dilution. How do we say that it decreases with dilution? It is because in specific conductance you have specific volume, you don't have specific amount of electrolyte, you have rather what? Specific volume. So if 1 cc of volume is there, right? Suppose initially you have taken 1 gram equivalent of solution. So in 1 cc that entire amount is in 1 cc only. Now if you dilute the solution, right, but still you have to take 1 cc of that solution only, right? So now you see that compared to the initial ones, you had more number of ions. If you have 1 gram equivalent in 1 cc only, the concentration is what? More. Now if you dilute the solution to say 1 liter, then what will happen? Number of ions in 1 cc is going to decrease, because for specific conductance you have to take only 1 cc of that solution. So in 1 cc compared to the initial stage, you will have lesser number of ions. So if number of ions are lesser, then obviously your specific conductance will also be lesser. So therefore specific conductance decreases on increasing the dilution, whereas equivalent and molar conductance increases, right? And temperature already we've seen. Next slide please. Then see, we've seen there in general, I told you that there will be increase in the conductance upon dilution, but you can also observe that different electrolyte, means weak and strong electrolyte, they behave differently. Differently in the sense that trend is same. Increase will be there for strong electrolytes also, for weak electrolytes also, but there are some features which are different. For example, you see that this is what? This is the graph for acetic acid. Acetic acid is what? Weak electrolyte. Weak electrolyte, you keep on diluting the solution, molar conductance is what? Decreasing, increasing, and near to this 0 concentration, this value shoots up, right? Suddenly. Now it becomes suddenly then what? Parallel to your y-axis, correct? So obviously it is going to meet, but then at some point which is defined as infinity. So it means for weak electrolytes there is increase in the conductance, but you will never get a limiting value of conductance by extrapolating, because this is not a straight line which you can extrapolate, right? So in case of weak electrolyte, increase is there, but increase initially is very less, and then suddenly there is more sharp increase, and then you will never get a point wherein this curve will meet your y-axis. So therefore, and the reason is also difference. In case of weak electrolytes, increase in molar or equivalent conductances because of more degree of ionization or dissociation, because in dilute solution they are going to dissociate to a greater extent, right? If you take 1 molar solution of acetic acid, you will have maybe probably 20% of that is dissociated, but you dilute the solution, the dissociation will be more, and maybe you can have 40% acetic acid which is dissociated. Now you can even dilute it further, you may increase the degree of dissociation, and finally you expect that at 0 concentration, means final dilution, you should get the maximum value of lambda, that is called lambda m infinity, right? But you are going to get at infinity. So therefore for weak electrolyte, the reason is that on increasing the dilution, more and more number of ions are produced in the solution because dissociation is more. But in case of strong electrolytes, what do you see? You see that for KCl, actually this is not so, in this figure it's not, the slope is not that much. Please move back to the previous slide. It is more clear here. You see that this kind of straight line is there. This is for strong electrolyte, right? So what do you see? That in case of strong electrolyte also you observe an increase in the conductance, but the increase is not because of increase in number of ions. Why? Because number of ions are already, it has already dissociated to 100% extent. So you can't expect more number of ions on dilution. So what is the reason then, right? So the reason is that on increasing the dilution, you make the dilute solution, still if you have a larger number of ions in a small volume, then number of intermolecular interactions or intermolecular interactions are what? Strong, right? So if instead of that you have same number of ions in larger volume, then those attractions become what? Weak. So increase in strong electrolytes is because of weakening of intermolecular attractions, right? So increase is there, weak may be hai, strong may be hai, but the reason is different. Reason is also different and the trend is also slightly different. Trend is that in case of strong electrolytes, it is possible to extrapolate. You may get like this, but zero obviously, zero, you know, practically it is not possible. Zero concentration of an electrolyte means you have plain solvent, right? So solvent will have very less concentration, so you hardly measure the conductance of that solution. Rather what you do, that maybe 0.1 up to 0.2, see this is 0.2, maybe 0.001 you can measure, and then you can extrapolate that curve. It will meet the y axis, that is called lambda m infinity. So in case of strong electrolytes, it is possible to get lambda m infinity, next slide please, from the graph itself, but in case of weak electrolytes it's not possible. So this trend, I was telling you na, that you plot root of concentration. So strong electrolytes, they follow this equation. This is called Debye-Huckel theory, right? Debye-Huckel equation also, which says that lambda m at any, lambda mc means molar conductance at any concentration. It is given by lambda m infinity minus a root c. Lambda m infinity means its maximum value, then the value at infinite dilution. So see, in some of the books it is written as 0. 0 means at zero concentration. If I write infinity means infinite dilution, right? So you know, and then minus. So from this you can see that this quantity we have plotted what? Lambda mc only. So lambda mc is what? You know, if concentration increases, this what will happen to this value? Decreases. This is what we are seeing here, right? So you plot this. So it is in accordance with this particular equation. So strong electrolytes, they follow Debye-Huckel theory. Weak, they follow some other theory which will be, you know, we'll be discussing, that is they follow their limiting value cannot be found, so we need a special law which is called Kohlrausch law. Next slide please. Correct. So this law says that at infinite dilution, right, at infinite dilution, when there are no interionic forces or no we don't say intermolecular forces, at infinite dilution when there are no interionic forces, at that point each ion move independently of the other. Each ion will move independently of it, because see, if there are some forces which are pulling the ion back, then obviously the speed with which actually it should move will be lesser than that. But I am saying at infinite dilution. At infinite dilution means they are sufficiently far apart. So it means there are no intermolecular. By infinite dilution you mean this only. Somebody can ask you this thing also, that what do you understand by infinite dilution? You can't see the infinity point. Can you see the infinity? You can't see the infinity. Then how will you be sure that infinity has reached, this lambda m infinity has reached? What do you mean by infinite dilution? Decreases, not decreases, it means, see, I tell you, you perform a simple experiment. You take a solution, measure its conductance, right? Conductance is measured, dilute the solution, again measure the conductance. Conductance will increase, again dilute the solution, again measure the conductance. It will decrease. You keep on diluting the solution until you observe that there is no further increase in the concentration. You will call that point as your infinite dilution. ऐसा नहीं है कि you will reach infinity and you will see that what is going to be the value of lambda at infinity point. It's not like that. Practically, the infinite dilution means which will cause no further increase in the concentration upon dilution. That is infinity, right? So at that moment there are no interionic forces. If there are no interionic forces, then that means each ion can move independently of each other, right? So when they independently they are moving of each other, then that means their molar conductance will be sum of their molar conductance of individual ion. So total molar conductance of any solution, that is lambda m infinity, will be given by what? Sum of lambda m infinity of cation as well as lambda m infinity of anion. This V plus and V minus I have referred, these are number of cations and anions that you have in the solution, because it is not necessary that always you will have 1 by 1 electrolyte, 1:1. It means for NaCl, HCl, you will have simple equation that lambda m infinity for NaCl will be lambda m infinity of Na plus ion plus lambda m infinity of Cl minus ion. But for like H2SO4 you have, right? So then the number of cations and anions, they are not going to be the same. Therefore you need to put these stoichiometric coefficients, right? These are your number of anions and cations. And moreover, you need this law in order to calculate the lambda m infinity of what? Weak electrolyte. So weak electrolyte, how can you calculate the lambda m infinity of weak electrolyte? You make use of the quantities which are known to you, right? Known to you, what are known to you and what are easy to measure is the lambda m infinity of strong electrolytes. So you can express it in terms of what? That if you want to calculate it for, say, this is simple expression that for HCl it can be written like this. No, next slide please. But if for acetic acid you want to calculate, then you know that acetic acid, acetic acid means acetate ion plus H plus ion. So net you need only those ions, right? So what do? Indirectly you calculate with the help of strong electrolytes. You can say take the difference of sodium acetate. Sodium acetate will give you what? Acetate ion and sodium ion. Then you can add the molar conductance of HCl. HCl will give you H plus and Cl minus ion and minus NaCl. So making this modification, all those quantities will get cancelled and net what will you have? H plus ion and acetate ion. So therefore you can, so because all these are what? Sodium acetate, HCl, NaCl, these are what? Strong electrolytes. They are strong electrolytes, so that means their lambda m infinity can be easily calculated, and they've been already calculated and tabulated, right? So for each cation and anion, the values will be given to you and you can calculate like this way. And then we have, this is the main application of Kohlrausch law that for which it was actually formulated, right? And then we have other applications of this law also. One is your degree of ionization. We've been talking about degree of dissociation, to what extent. So how do you define the degree of dissociation? It means the extent to which any electrolyte is dissociated, right? It may be 100% dissociated if it is a strong, but then if it is a weak, then we define. See, for strong you never define alpha. Make sure this thing, that if somebody asks you that calculate alpha value for HCl, for KCl, for NaCl, immediately your answer should be that alpha is not defined for strong electrolytes. You can't calculate, it is always 1. So you don't define degree of dissociation for strong electrolytes, right? So for weak you define alpha, right? How do you define alpha? It is obviously the dissociated upon undissociated. Degree तो आप ऐसे ही calculate करोगे ना. So it can be calculated like this way. So what you can do that it is actually, I think by mistake I wrote equivalent, but this is given by the molar conductance at any concentration divided by the molar conductance at infinite dilution. Because what do you expect for weak electrolyte? That at any concentration it should be lesser than the infinity value, right? So the ratio is going to be less than 1 always. The correct is that you have alpha, which is lambda mc divided by lambda m infinity, right? Knowing the lambda, so lambda mc you can measure, वो तो easy है आपके लिए measure करना, and infinity you can make use of Kohlrausch law. So this is one application of one more application of Kohlrausch law that you have, that you can measure this denominator by using this law, and then finally you can calculate alpha value. Alpha value is very, very important. It tells you about how to how much extent it has been dissociated, right? Next slide please. And then you have ionization constant, right? So I've already discussed with you that if there are some weak electrolytes, if weak electrolytes are there, they are always in equilibrium with their ions, right? Suppose you have AB. So if it is weak, then obviously you are going to have equilibrium between A plus ion and B minus ion. It means it is not fully dissociated. So if initially C is the concentration of AB, right, you've taken, then alpha you say that it is the degree of dissociation. If alpha is the degree of dissociation, then how much of A plus ion you are going to get after the dissociation? C minus C into 1 minus alpha. It's actually, you can assume that suppose if AB is there, A plus B minus is there, if you take 1 mole of this, then if alpha is the degree of dissociation, you are going to have 1 minus alpha, 1 minus alpha, because alpha, if it has been dissociated, what is the left concentration? 1 minus alpha, 1 minus alpha, and if you have taken C, then you multiply entire thing by C. So therefore if you take C molar of AB, you are going to have C into 1 minus alpha, C into 1 minus alpha, that is what I have written here. Means C alpha will be formed, and C into 1 minus alpha will be, I'm sorry, I should have written C alpha, right? This is then C into 1 minus alpha, left, which is left dissociated is C alpha and C alpha, and undissociated is C into 1 minus alpha, right? So you take the ratio. So if any reaction, it is in equilibrium, you define what? Equilibrium constant, and in this case you will call it what? Because the reaction is what? Ionization, you will call it ionization constant. So ionization constant will be given by what? The concentration of products divided by the concentration of reactants, and you see you get C alpha square upon 1 minus alpha. Alpha I have already discussed with you, that alpha how can you calculate? Lambda mc upon lambda m infinity. So if you can calculate alpha, you can also calculate this K, correct? I hope it is clear to you. Next slide please. And one more application is that determination of your solubility product. Solubility and solubility product of sparingly soluble salt. So there are some salts which are what? Sparingly soluble. Sparingly soluble means they are hardly soluble in the solvent. So solubility, how do you define the solubility first of all? How do you define the solubility of any electrolyte? How do you define the solubility? No, it is the maximum amount of what? Solute that can be dissolved in a given quantity of solvent, right? For some, you see that you can try at home also, that you take 1 glass of water, right? You put a spoon of salt into that, you see that it will dissolve immediately, right? You put another spoon of salt, then again it will dissolve, and you keep on putting more and more salt, but you will reach a point wherein it will not dissolve further, right? So that is what you call it as saturation limit. So it means there is always a maximum amount of solute that can be added to a particular quantity, right? So the maximum amount of solute that can be added into a specific quantity of solvent, that is called solubility, right? So if we define that solubility, so it means that some salts or some substances are more soluble and some are less soluble, you know that, right? So AgCl, for example, lead sulfate, PbSO4, they are called as sparingly soluble salt because compared to NaCl, which will dissolve immediately, if you try to dissolve AgCl, you will not be able to dissolve it so easily because of its interaction also, because you know polar like dissolve like, जैसे ही आपका polarity जो है वो कम होगा, solubility will also decrease, right? So AgCl, barium sulfate, sodium, this lead sulfate, they dissolve to a lesser extent, so they fall in the category of sparingly soluble salt. So it means for sparingly soluble salt, the saturated solution will have very less quantity of what? The solvent, solute. बहुत कम quantity से आपका solution जो है वो saturate हो जाएगा ना. So that means solubility is what? It is what? Less or more? Less, right? So you can calculate the solubility. You know this relation is there, right? Already, what is this? This definition of your molar conductance. Molar conductance is there. Now you see, solubility is different from concentration. Concentration, solubility. How it is different? Because concentration can be lesser than the solubility. Solubility is what? It is the concentration when saturation has reached, right? So it is the maximum amount, but concentration, it need not to be maximum, na? If you dissolve 1 spoon of salt in a glass of water, the concentration, you will call that it maybe some concentration of that solution, whatever it will be, you will say that this much is the concentration of that solution. But if you reach that point wherein you can no more dissolve, you know, salt, then you will call that particular concentration as solubility, right? So that is the difference. So but see, for sparingly soluble salt, whatever is the concentration, whatever it means, if very little amount can go into the solution, it means whatever amount has gone to the solution, that is its saturation limit only, right? So if it is its saturation limit, that means you can assume that the concentration is equal to what? Though concentration is equal to the solubility itself. So means molarity is equal to the solubility in case of, because see, you cannot dissolve more solute into that. So therefore these two terms are equal. If instead of this you have solubility, then solubility can be calculated. This quantity, from where you can calculate this quantity? Kohlrausch law. So weak electrolyte के लिए you can calculate any electrolyte, not that ki solubility, but we are talking about. So if this for AgCl you can calculate by using Kohlrausch law. And then specific conductance you can measure from the instrument, means you measure the conductance, convert into specific conductance, take this quantity from Kohlrausch law and you get the solubility, right? We will see some examples. Next slide please. See, this is very simple example wherein a decinormal solution of NaCl has specific conductance equal to this, and then the ionic conductance of individual ions are also given to you. You have to calculate the degree of dissociation. This is one example of your Kohlrausch law. So it means, so you look at the quantity which you need to calculate. You need to calculate what? Alpha. If alpha you need to calculate, first of all write the expression for alpha. What is alpha? It is lambda mc upon lambda m infinity. So then see what are the quantities which are given to you. So given to you means it is given to you the normality of the solution. So it means you need equivalent conductance. So equivalent conductance of 0.1 decinormal 0.1 normal solution is given to you, right? So normality is given to you. You can calculate the equivalent conductance. Specific conductance is given to you. Kappa is given to you. Normality is given to you. You can calculate equivalent conductance by using this relation. If you know the equivalent conductance, and equivalent conductance of individual ions are also given to you. So you can calculate, but this is at what? At infinite concentration. So you can use Kohlrausch law, take the total, and alpha will be what? This value, equivalent conductance at any concentration divided by at infinite. So you get this. This is 0.85, right? So it means the degree of dissociation is what? 85%, right? Next slide please. This is also, you know, I think we've already discussed that how do you calculate it for a weak acid or weak base. You can, with the help of Kohlrausch law and known quantities, you can calculate. Next slide please. And then this I've taken the example of again AgCl solution, for which you need to calculate the solubility, right? Find its solubility. So their molar conductance at infinite dilution are given to you. What you can calculate from there? Lambda m infinity. If you can calculate lambda m infinity, you can calculate the solubility also, right? So these are the different types of you know, questions which can be asked to you, that concentration will be given to you and then you have to calculate this. Next slide please. The next portion. Now see, everything we've discussed about molar conductance, equivalent conductance, specific conductance, I hope they are clear to you. Kohlrausch law, its applications and all. Now the next part is, that is your electrolysis. It is the counterpart of electrochemical reaction that we've already studied in the last class, right? I told you that electrochemistry is it deals with the changes in transfer of electrons, right? Redox reaction. So it means in the previous class we discussed about the production of electrical energy as a result of chemical reaction, right? But chemical reaction there was what? Spontaneous. Now I told you that time also that this electrical energy which has been generated as a result of your redox reaction, you can utilize that energy to carry out the reaction which is non-spontaneous, right? So therefore we are now discussing the latter part of your electrochemistry, that is electrolysis. Electrochemical changes we've already discussed, and these are electrolytic changes. So we must know that how do we define electrolysis. So it may be defined as a process in which the individual the electrolyte is dissociated into ions when electricity is passed through their solution. It is not necessary that you always take the electrolyte in solution form, you can also take its molten form. So you include both. If electricity is passed through either aqueous solution or the molten state of an electrolyte and it dissociates into ions, you call that process as electrolysis. Now these are certain features. So this is the apparatus which is used to carry out electrolysis. This is called as electrolytic cell. Now electrolyte is taken from in the aqueous form or solution form, that already I have discussed with you. Now you see that the major difference that you have here is because this particular cell cannot be operated without the help of external battery, because this is what? A non-spontaneous reaction. So therefore it cannot occur on its own. You need to supply energy, and that energy will come from what? External battery. So that means you are connecting an external battery and then allow the electricity to pass through the solution, and then it will dissociate into ions. So therefore the difference is here. See, the basic phenomena is your redox reaction only. So you will obviously have your cathodic half and anodic half. So the thumb rule says that at cathode always reduction takes place, and at anode oxidation takes place. It is going to be the same, but the polarity of cathode and anode are going to be different, opposite in this case. Why? We call cathode, otherwise there we define cathode was it was what? It was positively charged. Positively, why positively charged? Because electrons were being consumed there, right? Copper 2 plus ion is there, it is gaining 2 electrons, becoming copper metal. So electrons are being consumed there, so therefore it is deficient of electron and hence positively charged. But here we do not assign this polarity on the basis of electron, we assign the polarity on the basis of the poles of external battery to which they are connected. An external circuit, you have different sign. The cathode is connected to negative pole of the external battery, therefore it is negatively charged, and anode is connected to positive pole of the external battery, therefore it is positively charged. And here again the direction of flow of current will also be different. There current flows from what? Electron flows from anode to cathode, so therefore current flows from cathode to anode. This I am talking about electrochemical cell, but here current will flow from anode to cathode. I asked you that question there also, that in some of the exams it has been asked that what is the direction of the flow of current in the external circuit. So this is external circuit only, right? Next please. So this is actually the redox reaction that is taking place when electrolysis of any salt is carried out. For example, you can take, I told you that you can take aqueous solution also, you can take molten state also. Now suppose you take molten sodium chloride. Now sodium chloride example, why do we take it again and again? Because one is that it is a very good example because it exhibits it, the electrolysis can happen in both the states, molten as well as aqueous state, and the two are different, right? So both the phenomena you can understand with this example very well, that if you take the molten state, it means molten state means you only have NaCl, right? So no water is there, no aqueous solution, no water is there. So molten state of NaCl if you take, then what happens, that here you will have cathode. What happens at cathode? Reduction only. So if you pass the electricity, obviously what will happen? First of all, NaCl will split into Na plus and Cl minus. Now those ions are there in the solution. Now if ions are there, obviously they will not remain full roaming here and there. They will look for some, if cations are there, they will look for electrons to combine, right? So at cathode, sodium ions, they will combine with what? Electron, one electron, and will form sodium atom. Cathode में क्या होगा आपका? Reduction होगा ना? So Na plus plus one electron give you Na, and then anode पे क्या होगा? Oxidation. So your chloride ion, Cl minus ions are there, and those Cl minus ion, here I have written the complete reaction, otherwise what happens, that you can have chloride ion, right? Chloride ion will lose one electron to form what? Chlorine atom, one electron. This is what? Oxidation, right? So when this chloride and this one chloride atom, they will combine to give you Cl2. So I have written the net reaction actually, 2 chloride ion. So because you have to multiply it by 2. So it means you see here that one electron gives you one sodium atom, but 2 electrons give you one chlorine molecule, right. So the net reaction you can say, so it means at cathode you will have deposition of what? Sodium metal, and at anode chlorine gas is evolved. But if you take the same substance in its aqueous form, you can also take the aqueous solution of this NaCl. So there also you'll have some reactions which will take place in addition to these reactions, correct. Why? Because there you have water also. Competitive reactions will take place. You have water. Water can also be dissociated into H plus ion and OH minus ion. If H plus ion, so similar to Na plus electron giving you sodium atom, you can have here H plus also electron giving you hydrogen molecule, so multiply by 2, you'll right. And instead of this you can also have OH minus ion which are competing with this, but then you again make use of your electrochemical series that you've already learned, right. What? That reduction potential of whose is more, right. So here it has been seen that reduction potential of water is more compared to what? Sodium ions, means reduction potential of H plus ions is more compared to sodium ion. So therefore you get as a byproduct of molten sodium chloride, you get sodium metal and chlorine gas. But when you carry out the same reaction, electrolysis in its aqueous form, you will have Cl2 will remain same, but at cathode you will get H2 gas. Why? Because reduction potential of H plus ion is more, so they will preferentially undergo reduction compared to sodium. And oxidation potential of chloride ion is more compared to the oxidation potential of what? OH minus ion. Because what I am telling you, that at both anode and cathode you will now have a possibility of two reactions which are competing with each other. Here H plus plus 1 electron can give you half H2, that reaction can be possible, and here the oxidation of hydroxyl ion to give you H2O again, so O2 can happen, right. So which will occur, that will be decided on the basis of their potential. So when we talk about the reduction half, we will compare their reduction potential. Whichever is having more reduction potential will get reduced more easily, and at anode we are talking about the oxidation, so whichever is having higher oxidation potential will get oxidized preferentially. So H plus has more reduction potential, so therefore you will not get sodium metal as a result of the electrolysis of aqueous sodium chloride, but on anode this reaction will occur preferentially, right. Next please. Now electrolysis, you know that what is electrolysis, what is the basic thing, and finally we have Faraday's laws of electrolysis. Faraday studied the electrolysis in detail, and in order to till now we were talking about electrolysis qualitatively, right. So but how much electricity is generated, how much current is passed, that means we have to discuss the quantitative part of electrolysis also. So quantitative part of electrolysis was discussed by Michael Faraday, and he gave two laws, first and second. First law says that amount of chemical reaction which is taking place, it is directly proportional to the amount of electricity which is being passed. Or means you can also say that the amount of substance which is deposited at particular electrode, it will be directly proportional to the amount of current being passed through the solution, right. So it means if W represents the weight in grams, so it is directly proportional to Q. It means if Q coulombs of charge is being passed through the solution, then and W is the mass of the metal which is being deposited on the electrode, then W is directly proportional to Q. जितना आप इलेक्ट्रिसिटी पास करोगे उतना ही कोई मेटल आयन जो है वो उस पे डिपॉजिट होगा. And removing this proportionality constant, we put a proportionality sign, we put a constant here Z, and it has a specific name. It is called electrochemical equivalent. Sometimes you are asked the difference between chemical equivalent and electrochemical. So here we focus upon electrochemical equivalent only. Now you can define very easily if Q is 1, W is 1, or if Q is 1, Z is equal to what? W. It means if 1 coulomb of charge is passed, then amount of substance which is being deposited is known as your electrochemical equivalent. Or you know that Q is what? Charge, and charge is what? Charge is current into time. So if 1 coulomb of charge is passed, it means 1 ampere of current is passed for 1 second. So it means electrochemical equivalent can be defined as the amount of substance which is being deposited at any electrode when 1 ampere of current is passed for 1 second. Right? If number of, you increase the number of coulombs of charge, obviously there will be more amount of substance that will be deposited. Next slide please. And that we can see from this example that find the total charge. You can find out the total charge on N3 minus. So N3 minus, so that means 1 gram substance is given to you. Charge you have to, it means this much is being deposited. To deposit this much of ions, substance on the electrodes, how much charge you require, that is what we have to calculate here. So it means we need to find out how many number of moles, because I think last class maybe we discussed what is F, how do you define F. F is charge on 1 mole of electrons. So if 1 gram, it means you need to convert it in number of moles. So number of moles, so you divide gram divide by molecular mass, right? So 1 by 14 you calculate the number of moles. Now number of moles if you calculate, and then you have electronic, you see the charge on this is 3 minus. So total charge will be what? This quantity is what? F only. This is F only, na? This and this, you multiply this quantity by this quantity. What is this? Charge on 1 electron, this is what? Number of electrons in 1 mole. So you have what? This is F. So 3F. Basically you require, in order to deposit 1 mole of N3 minus, you require 3 Faradays of electricity. So therefore, but how many moles you have? You don't have 1 mole here, na? You've calculated mole here. So therefore you need to multiply this by number of moles, and therefore you get the charge. Correct? Next please. Here also I think the similar problem is there, you can solve. If time permits I will discuss it later. Next please, skip this also. Next. Now we have Faraday's second law, right? So Faraday's second law says, it provides a very easy method that to calculate the amount, again to calculate the amount of metal which is being deposited at different electrodes. So it says that if same amount of electricity, suppose you have different electrolytes are there and you connect them in series, you pass the same amount of charge or same amount of electricity through them, correct? Then you want to see whether the same amount is being deposited on each electrode or not, right? So you'll obviously that you will expect that if 1 coulomb of charge is being passed through the solution, the solution you can have copper sulfate solution also, AgNO3 solution also, H2SO4 solution also, but do we get the same quantity of substance which is depositing on the electrodes? No, because this will have some relation to their chemical composition also. And what is the composition? Means their equivalent weight. So it means, it says that the weight of substance, if same quantity of charge is passed through the solution in series, then weight of substance deposited is directly proportional to its equivalent weight. So W1, if you have two solutions, then you have W1 is representing the weight of first component that is being deposited. It will be proportional to what? E1, and W2 is proportional to E2. So you take their ratio, so W1 is equal to, and W, you know that it is what? ZQ, further can be written as ZI. So ZIT, and I and T is same because same charge you are passing. So it can be further written as Z1 upon Z2 is equals to, so electrochemical equivalent will also be proportional to their equivalent weight. And equivalent weight, you know that it is given by what? Molecular weight divided by number of, equivalent weight I am talking about, number, it is molarity divided by the number of electrons which are transferred, or if it is acid you divide by basicity, base you divide by acidity. You know how to calculate the equivalent weight, right? So this is, here we can take an example. You see that if you have copper sulfate solution and silver nitrate solution in series, right? So how will you decide that how much of charge is required for any? You are passing the same charge, but same amount of silver and same amount of copper will not be deposited on the respective electrodes. How can you account for that? You see that if you consider the reduction of sodium ions, in order to get one atom of sodium, you need only one electron. So therefore, if you have 1 mole of sodium ions, you will get 1 mole of sodium atom, right? So it means if 1 Faraday, so that means 1 Faraday is required to deposit what? 1 mole of sodium. But you see that if you have copper, in order to deposit 1 copper atom, how many electrons you require? 2 electrons. If 2 electrons are required, that means 2 Faradays of electricity is required. That means if you pass 1 coulomb of charge, then sodium will be deposited, amount will be 1 only, but copper will be 1 by 2. And similarly, aluminium requires 3 electrons, 1 by 3. The amount will be different, because if charge is more number of electrons are required to convert them to neutral atom, then obviously more charge is required. Indirectly what we are saying from this equation, that more charge is required, right? So therefore 1 mole of electrons can produce 1 mole of sodium, but 2 mole of electrons can produce 1 mole of copper, and 3 moles of electrons can produce 1 mole of aluminium. So it means the number of electron involved, n here is number of electrons. If n number of electrons are involved in the reaction, you require n Faraday of electricity in order to deposit what? 1 mole of that substance, correct? So we have an example here. Next please. How much charge is required? This is very simple, similar to what we have done just now. That reaction is given to you, you have to find out the charge, right? So if 1 mole of, 1 mole of aluminium, 3 plus 2 aluminium. So you have to just see how many electrons are required. So 3 electrons are required. How much charge you require? 3 Faradays. So Faraday constant, you know the value 96500. So you can calculate the charge. Now for copper, you require 2 electrons, so 2 Faradays is required. MnO4 minus 2 Mn2 plus. You see the change in the oxidation number. MnO4 minus, what is the oxidation state of manganese in this? It is plus 7. Because oxygen you have 2 negative, na? 4 oxygen minus 8, altogether you have plus 7 here. So it is going from plus 7 to plus 2. So that means how many electrons are required? 5 electrons. So therefore the charge will be 5F. Next slide please. Now how much copper will be deposited on the cathode of an electrolyte containing copper sulfate by the passage of, now here they are asking you how much weight, how much gram of copper will be deposited, but Q is being given to you. In the earlier problem Q, you had to calculate Q. Here you are given that what is Q, right? Because Q, how Q is given, current is given to you, time is given to you. If these are given to you, you can calculate Q, right? So from current and time you can calculate this much. So it means 3600 coulombs of charge is being passed. Okay? Now reaction require 2 electrons. So that means in order to deposit 1 mole of copper, you require 2 Faradays of charge. So that means 2 Faradays of charge is equal to 1 mole of copper is equal to, 1 mole is equal to how much? Molecular mass of copper 63.5 grams, because in grams, because is asked in grams कितना ग्राम आपका जो है वो deposit होगा. So if 2 Faradays can deposit this much gram, then you can calculate that 1 gram will be deposited by means this much charge. So because 2 Faraday can deposit this much, but your charge that you are passing through the solution is not 2 Faraday, it is how much? 3600 coulomb. So if 2 Faradays can deposit this much, then 36 will be what? 63.5 divided by 2F into 3600. So this much of copper will be deposited. Next please. And then this is the thing here, instead of you see that nothing no quantities in terms of their values are given to you. You just have to take their respective ratios and you can find out. Electrolytic cell, it has ferrous chloride and ferric chloride, right? And what will be the ratio? Right, ratio of their masses which are being deposited. So you know that ratio is what? W1 is proportional to E1, W1 upon W2 is equal to E1 upon E2. So E1 is what? M upon number of electrons exchange. So if ferrous chloride is there, it means iron is in +2 state, right? So you require 2 electrons. So therefore molarity will be divided by what? 2. And in ferric chloride, the oxidation state of iron is 3. So you'll divide by 3. So M by 2 divided by M by, so therefore you'll have the ratio is, so it means ferric chloride जो है ratio of iron deposited will be, it's like 3 times then the 3:2, right? So next please. This is the example I think we've already discussed, right? While discussing the electrolysis of sodium chloride, I have discussed with you that what are the products of molten and aqueous sodium chloride electrolysis of this. So reason also I have discussed with you based on their reduction potential. Now this can also be conceptual question. What is the free energy of a galvanic cell and electrolytic cell? Galvanic cell, because it involves a spontaneous reaction. For spontaneous reaction, delta J is what? Less than 0, it is negative. And since electrolytic cell required, they involve non-spontaneous reaction, so delta G is positive in that case, right? So I think with this that is done, and if you have any doubt you can discuss, else I will discuss something else. No questions? केमिकल इक्विवेलेंट जो है आपका इलेक्ट्रोकेमिकल इक्विवेलेंट यहाँ पे है, बट इलेक्ट्रोकेमिकल इक्विवेलेंट इलेक्ट्रोकेमिकल तो we've already defined, and chemical equivalent is in terms of chemical reaction, that how much chemical reaction can be carried out, right? And that's there. I think we can go back to some problems that we had skipped previous videos. And before this. Yeah. How many atoms of calcium will be deposited from the solution of calcium chloride by a current of 25 milliamperes? So current is given to you, right? So it means I is given to you, time is given to you, you can calculate Q, Q you've calculated, so you have to calculate how many atoms of calcium, right? So atoms means more, how many, so you know that number of Faradays of electricity being passed is how much? 25. This is what charge, current into this, divide by F. You get number of Faradays. So number of Faradays, you require 2 Faradays in order to deposit calcium, because calcium is also calcium 2 plus 2 electrons. So you require this much to deposit 1 mole of copper, calcium, right? So atoms, you need to multiply in 1 mole, you have Avogadro number of atoms. So therefore these many moles, if there are there, you will have to multiply this by Avogadro number and you get those many atoms. Is it clear to all of you or not? Right? Then previous than this. This is, I think, very much clear. No need. Already discussed, and I think I skipped few things while discussing. We can go back to the previous line. Previous. Not this slide, but then you may be having some numerical problems based on calculating their degree of dissociation also, that the concentration is given to you. You have to calculate the ionization constant, right? And means to combine or to summarize, what we can say that formula wise, we have quantitatively we've discussed what Faraday's law उनका formula है. Based on those laws you may have questions like numerical problems may be asked to you, and then you may have questions based upon their lambda m infinity, means conductance, how to calculate the molar conductance, specific conductance, equivalent conductance, right? And then their their relation with the specific conductance. So one thing I wanted to discuss beyond this thing, that I told you that sometimes you take molten state, sometimes you take aqueous solution, right? It means you use water as a solvent, but you have to be careful. You must know that the water which we use here is a special type of water which is called conductivity water. The water which is used in conductance experiment is known as conductivity water, because though very small, but normal water has some conductivity. What is the dissociation constant of water? What is the dissociation constant of water? 10 to the power minus 14 kW, right? So water is also, it means 10 to the power minus 7, 10 to the power minus 7, you have H plus and OH minus ions are there. So it means even though to a very small extent water also dissociates. So if water also dissociates, then obviously it is going to conduct some electricity. Ions are there, right? So we do not want any interference into the samples calculation. So therefore we use the water which is like whose conductivity or conductance is very low, very low, right? So that special type of which is free from any other ions. Conductivity water is there, like which is free from any other ions, any other impurities, because it can have some other means some impurities also, because of which some ions can be there and they can also contribute to their conductance. So therefore you need to be careful while doing your conductance experiment. Okay, so I shall stop here. To answer this, So hydrolysis means, the term hydrolysis means when water breaks into H plus ion and OH minus ion. We define degree of hydrolysis means if you have a sample, right, so to how much extent it can react with water, you know, so water will split into, as a result of hydrolysis, will split into H plus and OH minus ion there. So if cation is there, then it will combine with OH minus ion. So suppose you have calcium ion, magnesium ion, so they will combine with what? OH minus ion component of the water and will form hydroxide. And if on the other hand you have anion, it will combine with H plus ion. So it means water breaks down and reacts with your sample. That process is called hydrolysis, and to which extent that process is happening, that is called degree of hydrolysis. Just like degree of dissociation, if you change the process from dissociation to hydrolysis, you will call it degree of hydrolysis. Thank you.